So last time we talked about the ability of the cells in the SA node to, in a very autonomous way, generate their own action potentials. So my purpose on this block here is to help you understand how that happens. There's no magic here. So how can cells have a rhythmic generation of action potentials, generates on its own without being caused by something else from the outside? Well, it all is about the nature of the channels that are in the membrane that will determine how the cell membrane behaves. So one of the qualities of these pacemaking cells is that they don't have a resting membrane potential. So it's never static at one thing. It's always undulating. So this is what I want to talk about now. Now, you might need to do yourself a favor because I'm going to be referring to the earlier lecture I had back when we did action potentials for the neurology part of the course. And remember, I had a set of lectures on potassium channels. You might want to go back and take a look at those because I'm going to be referring to these various types of potassium channels in this lecture and also in coming lectures as well. So again, a lot of this depends upon your understanding of how potassium channels work. Okay, having said that, let's get into it. So what we have here is a trace of the membrane potential of these special pacemaker cells, and we're just going to say, let's assume this is cells in an SA node. So what I have here is potential of the membrane, and I have time here, and so the thing that you immediately realize is there's no resting membrane potential. I'm just having cycles. So let's walk through the channels to see how this works and who are the players involved here. Well, I think I want to go ahead and start in the middle, so I'm just going to start right there. So what do we have? As time goes on, I'm having a drifting of the cell membrane potential to be just ever increasing, less and less and less negative. And you can see that drift there. You'll note that the bottom, about as low as it gets is about 70 millivolts. And so it's going to drift a little bit less negative, a little bit less negative, a little bit less negative. So that means if the membrane is drifting less negative, that means I am moving charge across the membrane and that I am, in this case, having sodium flow in a very steady way, and the delivery of the sodium is causing the membrane potential to be less and less negative. Well, if sodium is moving through, then that means it has to be moving through some type of channel. So let's go ahead and just do the line. We'll do the line all the way down here just to keep track of what's going on. So the first thing I want to bring your attention to is going to be this guy right here. In illustration, it has IH. Now, most of the literature will have a different name or term for this, and so we're going to say, and you'll find it as IF. That's what you'll see it most of the time. I don't know why this author chose H, but IF is what you normally see in the literature. And the F stands for funny channels. And they're called funny channels because they don't allow passage of electrolytes or ions through the channel if the membrane is above 0. In other words, any positive potential of the membrane, these channels completely close down. So these funny channels are permeable to both sodium and potassium. They're more permeable to sodium than potassium, but they are permeable to both. So what you have here is the shaded area here it's below the line here. So when you have the shaded area below the line, what that means is that I'm having a net positive flow into cell. And in this case, what I'm having is sodium is just kind of flowing through these funny channels. Now again, why would the sodium flow in? Remember we talked about it's one thing to have a channel open, but whether or not an ion will flow through that channel is going to be contingent upon the forces acting on that. And remember we talked about your forces being your concentration gradient and then the electrical forces. And so you calculate that together, we come up with a Nernst value, and then that's going to give you a sense of what the end resulting force is when we take in consideration concentration gradient and electrical forces. So you'll recall that the Nernst value for sodium is, plus 60 in that range. So what that means is that I have a pretty powerful force driving the sodium in, because we have sodium is also way more concentrated on the outside of the cell relative to the inside of the cell, plus inside the cell is negative, sodium is positive, sodium wants the cell membrane to be plus 60. So you have a lot of force driving sodium into the cell, and it will do so through these funny channels. Now, again, these funny channels, they're just a little bit open to sodium, so you're not having this massive flow of sodium coming in, but you're having enough of a sodium dribbling in to just gradually bring this action potential, bring this voltage potential more and more positive. So you can see here I'm having, as the gray gets longer, that means I'm having more and more flow of sodium into the cell. Now, what else is happening during this phase? And by the way, we call this phase 4. Each of these has a number, so this is phase, let me go ahead and put the numbers in for you. This is phase 4, this is phase 0, and this is phase 3. So I got phase 3 over here, I got 0 here, and 4 here, just to get the idea. So I'm going to refer to these as phases. So phase, 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 and phase. So during phase 4, looking at the graph here, so we have sodium flowing in. This is going to be calcium, calcium, so calcium here, calcium. So no calcium's flowing in. I'll talk about the sodium-calcium exchanger later, but nothing's going on there. Oh, but notice here, I have these channels here, and these are going to be delayed rectifier channels. These are potassium channels, of course. And we talked about those in the earlier lecture. So what this is telling me here, now if the shade is above the line, what that means is that is indicating that positive flowing out of cell. So as far as potassium is concerned, because I have the positive here, then that means my net positive movement is out of the cell. So I'm having positive moving out of the cell. And remember over here, I said my net positive, and this is positive associated with sodium, my net positive associated with sodium is flowing into the cell. So what this is telling me is that I'm having sodium flow into the cell, I'm having potassium leave the cell. So I've got a swapping of a positive in, positive out, right? So if I have one positive sodium flowing in, one positive potassium flowing out, then that means there's no net movement in terms of the membrane potential. But what you see here is this is going in this direction here. What does that tell you? That tells you I'm having sodium flowing in, I'm having potassium flowing out, but my sodium inflow is exceeding my potassium outflow, leading to a net drifting of the membrane potential to be less and less negative. Also, what I have down here, and this is channel right there, and we talked about this in an earlier lecture, this is going to be my sodium channels that are going to be associated with acetylcholine. Okay, and we talked about that in an earlier lecture. And where the acetylcholine come from? Comes from my vagus nerve. Vagus nerve, that's part of my parasympathetics. So I'm having a continual vagal input into the heart, a parasympathetic tone or vagal tone. And so when that vagal tone is there, depositing acetylcholine, again, binding to those M2 receptors, which in turn is going to be through G proteins, causing opening of these potassium channels, again, in response to the acetylcholine binding to the M1 receptors. So I'm going to have some potassium leaking out as well. But even then, still, the sum of this potassium here leaving the cell is going to be less than the sum of the sodium going into the cell, which again results in a less negative potential. So you got that going on. Then something interesting happens, and that is right about here. Okay, and so we'll go down to some along in there. Something happens. Now I'm having a quick kick up here. So what's that all about? It's not the sodium that is doing this. Now something is different. And so the initial kick up is from this guy right here, and this is a T-type sodium channel, calcium channel. T-type calcium channel. And these are called transient channels, and they're transient because they open up very quickly and then they close relatively quickly. So they're going to allow calcium to come in. So this is below the line. So now I'm having calcium flowing into the cell. And then a little bit after that, I'm having my L-type calcium channels open up, allowing even more calcium to flow into the cell here. Now, mind you, I'm still having some sodiums flowing in, but the sodium flow, these funny channels, will begin to close off. Okay, you can see that there. But now calcium is carrying the day. So when I'm having these calcium flow in, and again, each one of them is carrying a 2 positive valence. So that's a pretty hefty charge flow in, and I have a lot of forces acting on the calcium coming in because I got way more calcium on the outside than I do the inside. In fact, the Nernst value for calcium is like in the 140 range, somewhere along in there, so it's really positive. So way more than even the sodium. So I have a lot of forces wanting to drive calcium into the cell. So that is going to cause a pretty good kick up in the increase. And so we're actually calling this an action potential. That is my action potential happens right there. And again, this is because of the flow of calcium. You'll recall in skeletal muscle, you'll recall in nervous tissue that the action potential was driven by sodium through these voltage-sensitive sodium channels. Here, the action potential is driven by these voltage-sensitive calcium channels. So it will head up, and then all of a sudden, then it starts going the other way. So we'll go, let's go blue here. So something happens here. So we'll straighten that out, and look what happens. Now I am heading back down. So what is happening here? Well, you'll note now the T channels have already closed, so I've shut that faucet off, and my L-type channels, they're starting to close now. Again, they're voltage sensitive, so I'm choking off the calcium flow in. But look what else is happening at this point. And of course, I've just basically shut off my sodium flow, and so it's not moving in. So what is kicked up is my delayed rectifier channel. So it is kicking way up here. And so now what I have is a flow of potassium leaving the cell in excess of any positive charge moving into the cell. So if positive charge efflux is exceeding inflow of positive, that means I'm driving my membrane potential to be more negative, and this is kind of where I am over here as well if I go to the next beat. So now I'm having lots and lots of potassium flowing out in excess of any sodium or calcium flowing in, bringing this back down to this trough here. Then what will happen is that the delayed rectifiers will then begin to close down. Okay, so we'll go ahead and just so we can see the cycle here, draw it over here, and we're going down there. So now my delayed rectifying potassium channels begin to close. Okay, and so now I'm at the bottom here. Now they've closed back down, reducing the amount of potassium leaving the cell. And now what am I left with? Now I'm back to my funny channels. The funny channels then begin to open, allowing more and more sodium in, and we start the cycle over again. So because I'm having these very specialized channels that open and close by their nature, we've set up this membrane to be continually cycling, which is really, really interesting. So if you got the right kind of channels with the right attributes, you can create a cell membrane that never has a resting membrane potential, but will always be cycling, having an action potential, and then going back and having another action potential, and so forth. So I think this is really, really, really slick. Now, a couple other things that I want to bring your attention to that I have not mentioned, one being here, this guy right here. Okay, this is a sodium-calcium exchanger, and this is in the literature. You're going to see this is NCX. Okay, this is an exchange pump, and so I'm just going to cartoon it out for you. And so what happens here is it can push a calcium out, and then it will pull in sodium. So I got that. That's the nature of that pump there. This is not an ATPase pump. So this pump is generated or spinning, pushing calcium out. And of course, you go back earlier in the course when we talked about Gibbs-free energy. And the take-home message of the Gibbs-free energy is there's no such thing as a free lunch. So the energy scheme has to balance out. So remember all of this calcium coming in through these T and L channels? Well, if the calcium is flowing in, you better have a way of kicking the calcium back out, or you're not going to be having a long-lasting cycling going on here because you're going to run out of calcium. Give it enough time, all the calcium ends up inside the cell. So I have to have a way of pushing the calcium back out. Well, as you'll recall, there's a lot of force driving the calcium into the cell. So that means I need to have a big energy source to push that calcium against its concentration gradient and against the electrical forces. This is where my sodium comes in, because as I'm sitting down here, in particularly the lower negative areas of membrane potential, remember, I have the sodium that wants to go in pretty bad. So I have a lot of electrical forces and concentration forces driving the sodium in if it can. Well, it turns out with the nature of this pump, it takes 3 sodiums to drive out 1 calcium. So the energy that is driving the ability to push a calcium out is going to be driven by the sodium concentration electrical forces driving the sodium in. So the sodium is flowing in and while it's kicking the calcium out. And so you'll note that I'm having a 3 to 2. Don't forget this is 2, so I'm having a 3 to 2. So again, I'm having a net movement. Every time this pump spins, I'm having a net positive going into the cell. And that's why this is in the below the baseline here. Because remember I said, if it's below the baseline here, remember we talked about the same thing here, that means I'm having a net positive charge moving into the cell. And that's exactly what's happening with this NCX pump. So this is the way you rectify the situation in terms of getting the calcium out. Now, one of the cool things about this pump, and we're going to see this later on, is that this is a reversible pump. So as long as I have a nice gradient of sodium, electrical forces and gradient forces, the sodium is going to be coming in. But if I were to have a different configuration where, say, the membrane is somewhat positive, now I'm losing my driving force of sodium coming in, this pump can actually reverse And again, actually, the calcium, okay, I will say then the calcium will go in, and it will kick out 3 sodiums, which is kind of cool. So this is a reversible pump. Now, what determines what direction this NCX pump will go? What will happen? It's basically a function of the membrane potential, and that will determine whether my energy is coming from the sodium wanting to flow in or the calcium wanting to flow in. But in this situation here, it's all about that configuration there. So now that raises another question. Okay, so I've taken care of the calcium, so I now know how to rectify the calcium that flowed in to kick it back out. What happens to all the sodium and the potassium? Because I'm having a potassium flowing out of the cell, and I'm having sodium flowing into the cell with these funny channels in this delayed rectifying channels and these acetylcholine channels. Well, don't forget our good old friend, my sodium-potassium ATPase pump. Sodium, and then potassium here. And of course, you got your 3 sodiums and the 2 potassiums here. But this is going to burn energy, so this is going to be my sodium-potassium ATPase pump. So that pump is not in this diagram, but this is going to handle the sodium-potassium gradients, trying to, again, realign the situation so that I don't run out of potassium and run out of sodium. So between the sodium-potassium ATPase pump and the NCX pump, they're the ones that are going to be making sure that the concentration gradients of these 3 very important ions are kept in the appropriate levels so that this system can continue to do what it does. Okay, so on the next page, I basically have everything I talked about laid out here for you. Maybe the wording is a little differently, but these are basically the points I've just talked about. So this is more of a summary. In case you want to go back and read through it, I advise you to do that in case I forgot something. But anyway, so this is kind of a summary of what's going on here. But this is really, I just find absolutely fascinating that you can, if you have the right kind of channels, that you can orchestrate this lovely dance of these electrolytes or ions relative to these channels that are opening and closing in beautiful rhythm of each other. Okay, so we will pick up on the next block next time.